All right, hey guys, we're going to talk today about Riemann sums. Um, so you guys have learned how to calculate antiderivatives for pretty simple functions. And today we're going to talk about how the antiderivative relates to the area under the curve and how we can approximate that area using rectangles. And so if you were to calculate an antiderivative for this function that I have here, x squared plus x, you guys know that you would just kind of do a backwards version of the power rule, and you would end up with, I think, 1/3 x cubed plus 1/2 x squared. And then if you were to evaluate that function from, say, 0 to 4, like what I have in this graph right here, then you would actually end up with the area that is underneath this curve. This area has a lot of applications because it gives us the ability to calculate area when we have something that maybe we can't use a geometric formula for. So before we can really understand the idea of antiderivatives as area, we want to learn how to approximate this area. And we're going to do that using tiny rectangles. And in this case, in this picture, they're actually not going to be too tiny, but so these rectangles are called Riemann sums. And so what's going to happen is we have kind of four methods that we can use. Um, One is what we call a left Riemann sum, and generally it's denoted by this notation LRAM. That would be left Riemann approximation something. And then we left RAM or a left Riemann sum. What happens is say I have this function right here, which is x squared plus x on the interval from 0 to 4, and I want to approximate the area underneath this curve between it and the x-axis. And so for a left sum, what's going to happen is we are going to take and we're going to make rectangles. And the height of our rectangle is going to start at the furthest most left point. And what you want to do is you want to take and break this into what we've called subintervals. And generally, you're given the number of subintervals that you would want to use. Let's start with an example. We want to do a left Riemann approximation with 4 subintervals. And so what would happen is we would take and we would start with the leftmost point. See that point right there? And then we would use that as the height of our rectangle, and then we would use the width of our rectangle as just the distance. Now, if we went 4 subintervals, then we're going to break it into 4 pieces. This is the interval from 0 to 4. And so we start at the leftmost point, and then we use that as the height, and then the width of our rectangle is just the length of one of those subintervals. And then for the next one, you can see I'm going to take the leftmost point of this interval, and that's going to be, I'm going to use that y value as my height, and then I'm going to calculate the area of that rectangle. For the next point, this would be, that's 1 and that's 2. I'm going to use the y value here, and then that's going to be the height of my rectangle. And then for the last one, I'm going to use the y value there, and that's going to be the height of my rectangle. And so this area right here, you can see, I'll shade it in for you, would be a left approximation for the area under the curve. And now this doesn't do a super great job of approximating area. You can see that we would say that this is under approximating because I'm missing all of this area right here. And so the value that I get is going to be an underestimate for the actual value. But it still can be helpful, and actually the smaller that we make these rectangles, the better estimate we're going to get, and then we'll talk about a few other methods that will give us a little bit of a better estimate. So let's go through and let me show you how to calculate this left Riemann sum. So the idea is you want to take and you want to basically just calculate the area of all these rectangles. So it's, just going to be length times width, or width times height, however you want to think about it. And if you'll notice, each one of these widths is the same. They all have a distance of 1. There's one there and so forth. So most of the time what's going to happen is we're going to take the width of that rectangle and we're going to put it on the outside because, every one of these heights is going to be multiplied by that width. And then we're just going to take and we're going to, we want to add all these areas together. So since we're multiplying all of them by 1 by putting it on the outside, then we're just going to take all the heights and we're going to add those together. So the height here of this first rectangle is just going to be the function evaluated at the left point. So this would just be f of 0 or y of 0. Let's call this f of x. The next point would be the height at 1, which is going to be f of 1. And then as you can see the pattern, the next is going to be the height at 2, which is going to be f of 2. And then the last one is going to be the height at 3, which is f of 3. So f of 0 is going to be 0. Just going to plug into my function. F of 1 is going to be 2. F of 2 is going to be 6. F of 3 is going to be, that'd be 9 plus 3, which would be 12. And so I would take all these things and add them together. That's 18 and 2, so that would be 20. So this left approximation would give me an area of 20 units under the curve. All right, so one of the things that's helpful to remember with left approximations is that you are, and this will make a little more sense when we talk about right, you include the leftmost point, but you exclude the rightmost point. And this is going to be true for all left approximations. All right, so now let's do the same thing, except now we're going to do what's called a RAM, or a right approximation. And so I'm going to take this picture here. Oh, I'm going to erase it all so I can draw on it again. So with right approximations, it's basically the same idea, except we are going to start with the rightmost point. So instead of making the height of this first rectangle the function evaluated at 0, now it's going to be the function evaluated at 1. So I'm going to go over like this. That would be the next one, the next height of my rectangle. And then at 3, that would be the next height of my rectangle. And then at 4, that would be the height of my rectangle. So now we're actually coming from the right, is usually how I think about it. So there's a right, there's a right, right, and right. And for this function, it is going to be an over approximation of the area under the curve. So let me go through and show you how to use the notation to calculate this, or how to calculate it. So we call it RAM. A lot of times you'll see it written like this, R sub 4, because we have 4 subintervals. And so this is just going to be the width of the interval, just like we did before, because we're just calculating the area of a rectangle, times the height of each one of these. So remember, the height of my first one is my function evaluated at 1, and so that's going to be 2. The height of the next one is going to be the function evaluated at 2, and that's going to be 6. The height of the next one is going to be the function evaluated at 3, and that's going to be 12. And then the last one is going to be the function evaluated at 4, and so that'd be what, 4 squared plus 4, so that'd be 20. Notice on this one, I don't include the first point, so I don't include the 0, but I do include the last one. So on a left RAM, you include the leftmost point, but you exclude the rightmost point. And on an R RAM, you exclude the left point and you include the right point. So here I'd get, what, 8 and 12 is 20, and 40 times 4, so this would be 40 here as an approximation. And so this would be an over approximation. So we have 2 others that do a little bit of a better job of approximating. One, let me erase this again, is going to be what we call the midpoint. And so if we were to notice how the left really under approximated and the right really over approximated. Well, what if we took and made the height at the midpoint between 0 and 1, and then we're going to get a little area under and a little area over, if you can see that line that I just drew. And then so the next one would be the midpoint of the next subinterval. And so I would use that as the height of my rectangle, the function evaluated at that value. And so I get that rectangle right there. And notice how I have a little over approximation there, and then I have a little under approximation there. So they kind of even each other out. It gives you a better estimate. And so this would be the next midpoint. be that rectangle, and this would be the last midpoint right here. That would be about there. And so this does a little bit of a better job approximating. So what we're going to do is we're still going to take the width of this rectangle, and each one of those widths is still just 1. But now I'm going to, instead of using 0, 1, 2, and 3, or 1, 2, 3, and 4, I'm going to use the middle point. And we call this MRAM. And so the width of each rectangle, is 1. And so now the middle point of my first interval is going to be zero point 0.5. So I'm going to do my function evaluated at zero point 0.5 plus my function evaluated at 1.5, because that would be the middle of my next subinterval, plus my function evaluated at 2.5, plus my function evaluated at 3.5. And that would give me my midpoint estimation. So if I go through and I find these values, if you have a calculator, a pretty easy way to do this is just to set up the table so you can ask. So my function evaluated at 0.5 is going to be, sorry about that, I'm kind of trying to use my calculator, it's going to be 0.75. My function evaluated at 1.5 is going to be 3.75. My function evaluated at 2.5 is going to be 8.75. And then at 3.5 is going to be 15.75. So now I'm going to take and I'm going to sum all these together. And I get 29, which seems to be a better estimate because it's kind of in the middle between the lower estimate and the upper estimate. Um, so this definitely does a better job. So the last one we want to talk about is the trapezoid rule. And so what the trapezoid rule is going to do is it's actually, instead of using rectangles, we're going to use trapezoids. And so remember, trapezoids have two parallel sides. So say I take this very first subinterval and I make those two sides parallel, and then I just use a straight line to connect. And then here, and this actually does a really good job of estimating, especially as the intervals get smaller and smaller. And so that would be my trapezoid estimation. Now you can use the formula for the area of a trapezoid, which is what you're going to do is you're going to add these two heights together. So say I wanted to do between 3 and 4. I would add these two heights together and I'd divide by 2, and then I would multiply by the distance, the width of the rectangle. But a really easy way to do trapezoid is just to average your left rim and your right rim. So this would be TRAM. I'm also going to call it T sub 4. And so the easiest way to do this is take L sub 4 plus R sub 4 and divide by 2. And so this is going to give me, what, 20 plus 40 over 2. So this would be 30. This gives me a pretty good estimate. And so the idea of what happens whenever you actually integrate and you or you find an antiderivative and then you evaluate it, say, between two numbers, is that you're looking at how these rectangles, you're actually taking the limit as the width of these rectangles go to 0. And we'll talk a little bit more about that next time. So I've shown you how to do it with a function, so I wanted to show you how to do it with a table also, because this comes up on the AP exam a lot. So I have this example here where I'm not probably just going to do R6, and, well, I could do all three of them, I guess. I want to estimate the distance traveled over 0 to 3 if the velocity is at half-second intervals as follows. So, if I have velocity and I want position or distance traveled, then I need to basically take the antiderivative. And so the easiest way to do that in terms of a table is to calculate your Riemann sum, because the area underneath that curve is going to represent the antiderivative over an interval. So if I wanted to do R6, let's start with that. Then I'm going to take and I'm going to look at the distance between all these intervals. And we're lucky that the distance between all these intervals is 0.5. But a lot of times on table problems like this, not all of these distances are going to be the same. So generally on table problems, instead of taking the width and putting it on the outside like I did with the function, because I know in that function that all my widths are going to be the same, I do each one individually. So I'll say, okay, um, I'm going to take this width right here from 0 to 5, and I'm going to multiply that, because that's the width of my rectangle, by the height. And anytime you're doing a right sum, you're going to take the right point or the right y value for those two x's in your interval. It's basically what you were doing graphically in the other picture. So here I have a width of 0.5, and then I have a height. I'm going to multiply that, sorry. I have a height of 12 plus, for the next one I have also another width of 0.5, and I have a height of 18. And then I have a width of 0.5 and a height of 25. And keep going, width of 0.5 and a height of 20. And then a width of 0.5 and a height of 14. And a width of 0.5 and a height of 20. And then I would just take and do all that math. So that would be what, 6, 9, okay, I'm going to screw this up if I don't get my calculator out. So I would get 54.5. All right, so left, you see on the green how every time I calculate that area, or the width times the height, my height is going to be the one on the right side. So when I do my LRAM, or my left approximation, I'm going to use the height on the left side. So my first interval, is going to be of width 0.5, but now I'm going to multiply it by that one right there. So I'm going to use the left point of the interval. So that's going to be 0.5 times 0 plus 0.5 times 12 plus 0.5 times 18 plus 0.5 times 25 plus 0.5 times 20 plus 0.5 times 14. And if I do all that math, I should get 34.5. And so that would be my left approximation. Now the last thing they asked me to do is the midpoint approximation. And so now they want me to do m sub 3. So what I'm going to do, remember the midpoint, you take your intervals, and if we want 3 subintervals, then these are going to be my 3 intervals. There's 1, 2, 3. Each one has a width of 1. And then I'm going to use the middle point. I'm going to use that y value, the function evaluated at that point, as the height of my rectangle. So this is going to be my MRAM, which is m sub 3, is going to be 1 times 12, because that's the function evaluated at 0.5, and then 1 times 25, and then 1 times 14. Oh, not 0.14, but 1 times 14. And so that would give me 12 plus 25, which is 37, and 14, so what is that, like 51? Which gives us a little bit better approximation. A few things to remember about Riemann sums, and these are questions that come up a lot, but if you're doing a left approximation, then if your function is increasing, then this is going to be an underestimate, just like the function that we saw on the previous example. If it's decreasing, it's going to be an overestimate. And then it's backwards for your RAM. If it's increasing, it's going to be an overestimate. And if it's decreasing, it's going to be an underestimate. And a lot of times, this I wouldn't try to remember, but I might just draw a picture because it was really easy to see on the previous page. I don't have it anymore. Whenever we did that left approximation, that this was definitely an underestimate, and whenever we did the right approximation, it was definitely an overestimate. All right. Well, I hope you guys learned something about Riemann sums, and I will see y'all soon.